This is the lecture on thermal expansion and heat transfer. So here we're going to be talking about energy transfer through heat. The first thing we need to consider is we have to define our terms. So we've already talked about work, which is a transfer of energy through a force, right? So work, remember, is a transfer of energy from one object to another object because of a force. Heat is another energy transfer. So in physics, heat refers to a transfer of energy from one object to another object or one place to another place because of a temperature difference between those objects. We use the symbol Q, capital Q, for heat, and Q is positive if energy is going into the object, and Q is negative if energy is going out of the object. The next thing we have to consider is internal energy. So we're defining internal energy as the energy associated with all of the atoms and molecules that make up a substance. So this includes vibrational kinetic energy of the molecules of a substance, and we talked about that a little bit before. It also includes potential energy associated with molecular bonds and things like that. So our kinetic energy, we can have translational kinetic energy, right? For instance, if we're talking about a gas, so that we have, right, independent molecules that are independent from each other, so that our gas molecules can randomly sort of move wherever, right? So we have translational kinetic energy of our molecules. We also have rotational kinetic energy, so that if we have a particular molecule that's spinning somehow, and vibrational motion of our atoms or molecules. So if I have a molecule where the molecular, right, so our molecule is made of two or more atoms, and then those atoms can vibrate, right? So then, or even vibrational energy between the molecules, for instance, in a solid where our molecules are all connected together. And again, internal energy, right, is proportional to the temperature of the system. And because internal energy is proportional to temperature, we're going to mostly be using temperature as a proxy for internal energy, particularly in the next lecture when we start talking about kinetic theory. Now, generally, heat, right, energy in or out of a system because of a temperature difference, generally speaking, heat changes the temperature of your object. So as long as your object is at a temperature that is not including a phase change, right? So if we have for a continuous phase, adding heat to your system or taking it away will increase or decrease the temperature. And the specific heat of a substance, specific heat of a substance, essentially tells us how easy or difficult it is to change the temperature. And it's specifically for solids and liquids defined as the amount of heat energy required to change the temperature of an object by 1 degree Celsius. And specifically the amount of heat energy required to change the temperature of 1 kilogram of an object by 1 degree Celsius. And so for physicists, the unit of specific heat is joules per degrees Celsius kilograms, or joules per kilogram degree Celsius. So it's the amount of energy required to change 1 kilogram of a substance by 1 degree Celsius. Now this is specifically for solids or liquids. For gases, it's not quite so simple. For gases, we have to talk about specific heat at a constant pressure or specific heat at a constant volume. Now, the other thing that heat energy does, right, that energy added or removed from a system by heat, is it can change the phase of an object. So if we are changing the phase, for instance, going from ice to water or water to steam or vice versa, then the heat energy required is equal to the mass times L, where L is the latent heat. And every substance will have a latent heat of vaporization. That's to go from steam to, gas to liquid or liquid to gas. And it will have a latent heat of fusion, which is the latent heat required to go from solid to liquid or liquid to solid. So we use this if we're undergoing a phase change. And again, this is the energy required to change the phase per kilogram. And then if we're just staying within the same phase and changing the temperature, we'll use this. Now we, in this class, are not going to be spending any time really dealing with phase changes, or this is called calorimetry. I know that chemistry hits that pretty hard, and so we're not going to really spend time on it. And so now that we've defined what heat is, energy transferred in or out of a system because of a temperature change, or because of a temperature difference, now we can talk about specifically how we can make that happen, right? So methods of doing this, right? So for work, the method is by a force. For heat, there are different ways to do it. And the most common ways, the main ways, are conduction, convection, and radiation. And so we'll take those one at a time. So when we talk about heat transfer, right, we can talk about power. Remember, power is the rate at which energy is transferred. So power, right, energy over time, right, dE dt. Now earlier in the semester, we only were dealing with work. So we defined power as dW dt, the rate at which work is done. We can also define power as the rate at which heat is transferred from one place to another place, because power is just, right, the rate at which energy is moved around. And if we're talking about heat, then power is Q, energy in or out because of a temperature difference over a time, right? So generally speaking, we'll have joules per second. The unit of that is watts. Now, our different mechanisms that we're going to be considering, again, are radiation, conduction, and convection. Radiation is an energy transfer, a heat transfer through electromagnetic radiation. So through light or any other electromagnetic radiation, infrared, ultraviolet, so on. Conduction uses collision of molecules within a substance to transfer energy. And so for conduction, you can imagine, right, if I have a pot sitting on a stove, the bottom of the pot gets heated by the stove, and that energy transfers, that heat energy transfers throughout the entire pot so that eventually the handle gets hot. That's conduction. Convection uses sort of bulk molecular motion to transfer energy. So for instance, boiling water, that's convection, and that is transferring energy, transferring heat from the bottom of the pot where the water is hottest through these, right, bulk motion of the fluid through the fluid to the top. So conduction typically, not always, but typically is through a solid or a liquid, and it's because of molecular collisions. Convection is energy transfer in a fluid, so liquid or gas, because of a sort of bulk motion of the molecules themselves. And so we'll take these one at a time. So radiation does not require physical contact between your objects. And every object whose temperature is above absolute zero radiates energy continuously in the form of electromagnetic waves. And this is because of vibrations of the molecules, right? So any object whose temperature is above absolute zero, the molecules of that object are continuously vibrating, and that causes them to radiate away energy. So for instance, if you turn on your stove, don't touch the stove, but just hold your hand over the burner, right? Don't touch it. Please don't touch it. But if you just hold your hand over it, even though you are not touching it, you can still feel that it's warm, and your hand temperature will increase even though you're not actually touching the burner. That's radiation. If you're in a room with a lot of people, and in the current times, please don't do that, but wasn't very long ago that we were all together in a big room. And when you have a bunch of people in a room, right, the room feels warmer because people are giving off what we call body heat. Again, that's radiation. Now, the rate at which this happens, and remember, rate of energy transfer is power. So the rate at which this happens is given by this equation, where E is the emissivity, of your object. And it's just a constant somewhere between 0 and 1 for your object. So an object whose emissivity is 0 essentially is a very, very shiny reflective object. It doesn't absorb energy very well. It also doesn't give off energy very well. An emissivity of 1 is what we call a perfect black body. This is an object that absorbs energy very efficiently. It also gives off energy very efficiently. Sigma is a constant given by 5.6704 times 10 to the minus 8th watts per square meter kelvins to the 4th. So it's very important here that our temperature is in kelvins. A is the surface area of your object. And then T is the temperature, again, in kelvins. And it's very important that your temperature be in kelvins here. And what we see is that larger objects radiate more energy, right? Hotter objects radiate more energy. The next method of energy transfer is convection. And convection is energy transferred by movement within a fluid, specifically within a fluid. And when this movement results from differences in density, it's called natural convection. So for instance, this is an example of natural convection. We have a radiator here, so we just have hot water traveling through these tubes, and this hot water, right, these hot tubes, your radiator, causes the air from radiation, causes the air around it to get warmer. And as the temperature of the air increases, the air molecules get further apart. So the density decreases, and as the density decreases, it moves up because it's lighter, right? Remember when we talked about fluids, things with less density tend to float. So this less dense air, this warmer, less dense air travels up. Now eventually it hits the ceiling, there's no other place for it to go, but there's more warm air coming up behind it, and that pushes this warm air away from the heater. And as it moves away from the heater, it cools, and as it cools, the molecules take up less space, and it becomes more dense. And as it becomes more dense, it falls, but it's continually being pushed by this warmer air behind it. So you get what's called a convection cell. And this is natural convection, and this cooler air gets pushed back towards the heater where it gets warmed, and the whole cycle continues over and over and over again. Boiling water is another example of natural convection. But sometimes you can also have forced convection. For instance, if I were to put a fan over here by this heater, that would force the air to move around and transfer the energy throughout the room more efficiently. And that's forced convection, when the movement is forced by a fan or a pump or something. The last method of energy transfer that we're going to be considering is conduction. And conduction, you have to think about this on an atomic scale. So if I have an object, right, and I put this side of the object in a fire. So I have fire over here. Right, here's my fire, and I put the left end of this bar in a fire. Now this bar has, right, it's made up of all of these atoms and molecules, and the ones over on the left side are going to be warmer because that side is in the fire. And so as they get warmer, they vibrate, and then they bump into the ones next to them and cause them to vibrate, and so on and so on and so on, all the way down to the right side, all the way down to the other end. And as this happens, right, these keep getting warmer and vibrating with bigger amplitudes and bumping the ones next to them and bumping the ones next to them. This energy is being transferred down my material until eventually this side, the right side of my rod, will get warmer, will increase in temperature. And the rate at which that happens, the power for conduction, right, is given by this equation. Where this K is called the thermal conductivity. And this depends on what the material is made of. So materials that are good thermal conductors, like metals, will have a large conductivity, and materials that are poor thermal conductors, for instance, if I stuck a wooden stick into the fire, it would take a much longer time, and also the wood would burn before the other side got hot. Whereas if I stuck a metal stick into the fire, it would hurt my hand before the metal melted or caught flames, a long, long time before. A is the area of contact. So, for instance, the area of contact would be, if I go back to the example of the stick in the fire, the part of the stick that's in the fire, the area of that part. L is the length of the material. So the length of the stick. And then TH and TC are specifically the hot side temperature and the cold side temperature. Now, another way we can think about this is if you think about a wall, right? So if I have a wall and I want to put insulation in my wall, right? I want my insulation to have a low conductivity. Now, if you are buying insulation, right, it's rated by something called the R value. And the R value is essentially the inverse of the conductivity. So a low conductivity has a high R value if, for instance, you're into construction or whatever, or you need to insulate your house. But let's say that I have, right, a hot side over here and a cold side over here. So here's inside my house, and then, right, I have inside my house. I want it to be warm because it's cold outside. And then outside is cold, and I want to keep the cold out and the warm in. So TH would be the temperature on the inside, the warm side of my house. TC is the temperature on the outside, the cold side of my house. K is the conductivity of my insulation material. Again, I want this to be small. A is the area of my wall, right? So it's this area of the wall, and L would be the thickness of the wall. And then the rate at which energy is moved in or out of my house, right, that's given by this equation. Now, for a house, you want this power, you want the rate at which this energy is transferred to be small. For other, maybe for other applications, for your frying pan, for instance, you want this to be large, right? You want the energy to get from the stove into your food quickly and efficiently. And this conduction can only happen if you have a temperature difference from one side to the other side of your material.